Welcome to our deep dive into exoplanets. You know those planets outside of our solar system?
Fascinating, aren't they?
Absolutely. And you've sent us a ton of research and articles. Our mission to go through it all and pull out the most mind-blowing facts about these alien worlds. We'll cover how we find them, the chances of life existing out there, and even the wild possibilities of us visiting someday. Get ready for some serious mind-blowing stuff, folks.
I'm excited to dive in. You know, it's crazy to think that just a few decades ago, we weren't even sure if there were planets around other stars.
Yeah, now we know they're actually more common than stars in the Milky Way. That's a lot of planets.
A lot of planets. More planets than stars, in fact. It really puts things into perspective.
But how do we even find these planets? They're light years away, basically invisible against the glare of their stars.
It's a huge challenge, like trying to spot a firefly next to a spotlight. But astronomers have come up with some pretty ingenious methods. One of the most successful is the transit method.
Transit method?
Yeah, so picture this. A planet passes between its star and us, like a tiny eclipse. Causes a dip in the star's brightness.
Ah, okay.
By carefully measuring that dip, we can figure out the planet's size and its orbital period.
So it's like a cosmic game of peekaboo. I read about another method in the research you sent, Doppler spectroscopy. Sounds a bit more complex.
It is a little. Imagine a dog walker being tugged slightly by their dog. You can't see the dog, but you can see the walker's movements, revealing that unseen force. Doppler spectroscopy is similar.
Okay.
A star and its planets orbit a common center of mass, causing the star to wobble slightly.
Got it.
And we can detect that wobble. Through changes in the star's light spectrum, these changes tell us about the planet's mass.
So by combining these methods, we get a more complete picture of the planet, its size, mass, even whether it's rocky or gaseous.
Exactly, like piecing together a puzzle.
Okay, so we found a planet, know its size, its mass, its density, but how do we know if it could support life?
That's the big question. The key is we're looking for life as we know it. Carbon-based, relying on liquid water. Alien life could be wildly different, but that's our starting point.
Makes sense. So liquid water is crucial. What else is essential? You mentioned the habitable zone, the Goldilocks zone.
Right, like a campfire. Too close, you get burned. Too far, you freeze. The habitable zone is that sweet spot. Around a star where the temperature is just right for liquid water to exist on a planet's surface.
Like Earth.
Exactly. Earth is perfectly positioned within our sun's habitable zone. Of course, life could exist outside of that zone, too. Some scientists believe subsurface oceans on icy moons in our own solar system, like Europa, could be more likely to harbor life than the surface of Mars.
Wow. So a planet needs liquid water, a good temperature. What else?
Well, a stable energy source, too. Could be light and heat from its star, or even internal heat from volcanic activity. This drives the planet's climate and geological processes, critical for life.
And it needs to be stable for a long time, right?
Absolutely. Billions of years for life to evolve. A planet needs long-term stability in its orbit and climate for life to take hold.
Makes sense. Enough theory. Let's meet some real exoplanets. Proxima Centauri b
Ah, yes.
orbits the closest star to our sun, Proxima Centauri,
Yeah.
just a little over 4 light years away. That makes it our closest exoplanetary neighbor.
Our nearest neighbor. But Proxima Centauri is a red dwarf star. They can be a bit volatile.
Volatile.
Yeah, they're much smaller and cooler than our sun, but known for intense flares and eruptions.
I did read about that. Wouldn't that be bad for life? Those flares would be pretty devastating.
That's a concern. Proxima b is technically within a habitable zone, but its star's unpredictable behavior raises questions about whether it could truly be habitable.
Okay, so maybe not the ideal vacation spot then. What about TRAPPIST-1?
Now that's an interesting one.
This one's part of a system with 7 Earth-sized planets. Imagine the view from one of those planets. Your sky filled with neighboring worlds. It's like a cosmic ballet.
It is. TRAPPIST-1 is an ultra-cool dwarf star, much smaller than our sun. All 7 planets are packed into orbits closer than Mercury is to our sun.
Being that close to their star, wouldn't they be incredibly hot? Are any even in the habitable zone?
Surprisingly, yes. 3 are thought to be in or near the habitable zone, including TRAPPIST-1. It's roughly the size of Earth. Potentially rocky.
That's exciting. Could there be life on these TRAPPIST-1 planets?
It's possible. However, red dwarf stars like TRAPPIST-1 can have intense magnetic activity. This could strip away a planet's atmosphere over time.
Oh, right.
We need more research to determine if any of these planets could hold onto an atmosphere and maintain a stable, habitable environment.
So there's potential, but we need more data. That
Yeah.
seems to be a recurring theme in exoplanet research. The need for better telescopes and instruments to really probe these distant worlds.
You're absolutely right. We've come a long way in just a few decades, but the quest to understand exoplanets and search for life beyond Earth has just begun. We're constantly developing new technologies and refining our methods to delve deeper into the mysteries of these alien worlds.
Well, speaking of alien worlds, let's talk about another intriguing exoplanet. Kepler 186.
Kepler 186, a remarkable discovery.
This one caused quite a stir back in 2014.
And for good reason. Kepler 186 was the first Earth-sized planet definitively found in the habitable zone of its star. It orbits a red dwarf about 500 light-years away.
Okay, so it's the right size and the right location.
Mm-hmm.
What about its atmosphere? Could it have liquid water on its surface?
That's the question, isn't it? Unfortunately, Kepler 186 is too far away for current telescopes to analyze its atmosphere in detail. We have very limited data, so we can't say for sure whether it has what's needed for life as we know it.
That's a shame. It sounds like a fascinating planet.
It is.
But future telescopes, like the James Webb Space Telescope, might give us more insights into its atmosphere.
Oh, absolutely. The James Webb Space Telescope is already changing how we understand exoplanets.
Yeah.
It can detect the chemical fingerprints of different molecules in exoplanet atmospheres, things like water vapor, methane, even potential signs of biological activity.
Amazing. So maybe one day we'll finally know the answer to that age-old question. Are we alone in the universe? But for now, it seems like the journey of discovery is just getting started. We're constantly finding new exoplanets, each one a unique piece of the puzzle, helping us to understand the vast diversity of planetary systems out there.
It truly is a remarkable time to be studying the universe. Welcome back to our deep dive into the world of exoplanets.
It's incredible to think there are so many planets out there, each one its own world. And we've only just begun to explore.
We really have. Every time we look deeper, we find even more extraordinary planets, challenging our assumptions about what's possible.
You mentioned earlier that we found some pretty extreme environments out there, like mini Neptunes. What exactly are those?
Mini Neptunes are fascinating. Larger than Earth, smaller than Neptune. They're thought to have thick atmospheres, hydrogen, helium, possibly with a rocky or icy core.
So like gas giants, but smaller. Could they support life?
Life on the surface is unlikely, crushing pressures, extreme temperatures. But some scientists theorize that if they have a lot of water, there could be a layer of liquid water deep below, maybe heated by internal geological processes.
A hidden ocean, trapped beneath a thick blanket of gas.
It's an intriguing idea, but really hard to study with our current technology. We'd need incredibly sensitive instruments to probe those deep layers.
Speaking of challenging environments, you sent me some info on ultra-hot Jupiters. Now, those sound intense.
But they are extreme. Gas giants that orbit so close to their stars, their temperatures can exceed 2,500 degrees Celsius.
2,500 degrees Celsius? That's hotter than some stars.
They experience intense radiation from their stars, leading to incredibly violent weather, supersonic winds. Some scientists even believe that metals can rain down from their atmospheres.
Metal rain. Okay, that's one experience I'd rather avoid.
I think we can all agree on that. These ultra-hot Jupiters push the boundaries of what we know about planets. They show the incredible variety of planetary systems out there, challenging us to rethink what a planet can be.
It's mind-boggling. The sheer scale and diversity of the universe. With all these incredible discoveries, how do we know the information we're getting about these planets is accurate? I mean, we're talking about objects that are light years away.
That's a crucial question. As we push the limits of what we can observe, there's always a risk of error. We have to be careful in our analysis.
So how do scientists guard against those errors?
One key approach is cross-validation. Whenever possible, we confirm exoplanet discoveries using multiple methods. If a planet is found using the transit method and the radial velocity method, that strengthens our confidence.
Like getting a second opinion.
Exactly. We also need to be aware of potential sources of error. Things like stellar activity that can mimic the signals of a planet. Astronomers develop models to filter out these false positives.
To make sure we're not seeing things that aren't there?
Precisely. And as our technology gets better, we can gather more precise data, refine our models, and ultimately paint a more accurate picture of these distant worlds.
So it's an ongoing process, always refining and improving our understanding.
Exactly. Science is all about constantly testing and refining our knowledge.
It really does feel like we're on the verge of a golden age of exoplanet discovery. But all this talk about distant planets and exotic environments makes me wonder, how has studying exoplanets changed our perspective on Earth?
It's been a profound shift. By studying exoplanets, we're forced to confront the vastness and diversity of the cosmos, shattering any illusions of our solar system being the norm. It's humbling, reminding us that Earth is just one tiny world among countless others.
It's a humbling thought, but also incredibly inspiring. It makes you realize that there's so much more out there.
Precisely. And it also highlights how important it is to protect our own planet. Earth is precious. And seeing how diverse and sometimes hostile other worlds can be makes us appreciate the delicate balance that makes Earth so special.
Okay, we've explored the diversity of exoplanets, from potentially habitable worlds to extreme environments. We've touched on the challenges of accurate scientific analysis. Now let's talk about the ethics of colonizing other worlds.
Yes, that's a big one. A topic that will likely be debated for generations. It's where science fiction meets reality, and it's full of ethical dilemmas.
Where do we even begin to unpack such a weighty topic?
Well, perhaps the most fundamental question is this. Do we, as humans, have the right to colonize another planet, especially if there's a chance of life already existing there?
It's like the prime directive from Star Trek. Should we interfere with other civilizations, even if they're just microbial life? Do we have the right to impose ourselves on another world?
That's a question that requires a lot of thought, a deep understanding of the potential impacts. We need to weigh the benefits of colonization against the risks to any existing life.
And even if a planet is seemingly lifeless, is it ethical to terraform it, essentially transforming it to suit our needs? Do we have the right to reshape another world in our image?
That raises questions about our responsibility to preserve other worlds. Is it ethical to impose our vision on another planet, potentially altering its unique characteristics, erasing its natural history?
It seems like every step towards colonizing another world raises more questions than it answers. And then there are the practical considerations, the technological challenges of establishing a self-sustaining colony.
The distances involved, the resources required, the long-term sustainability. Not to mention the unknown factors we can't even anticipate. These are daunting obstacles.
And let's not forget the psychological and social implications of having humans on another world. How would we adapt to a completely different environment, potentially isolated from Earth?
It's a fascinating area. It would require a radical shift in our thinking, our approach to society. We'd need to create self-sufficient communities, capable of surviving in an alien environment, potentially for generations.
It sounds like a social experiment as much as a technological one.
It really does. It raises all sorts of questions about how humans would adapt. Living in a confined environment, losing their connection to Earth, developing their own unique culture.
These are questions for scientists, philosophers, policymakers, for generations to come. But it's important to start thinking about these things now, as we explore the universe.
Absolutely. As we delve deeper into the realm of exoplanets, it's not just about scientific discovery. It's about reflecting on our place in the cosmos, our responsibilities as explorers.
And on that note, we'll wrap up part 2 of our deep dive. Don't go anywhere, though. In part 3, we'll explore interstellar travel and the idea of terraforming. Get ready for a wild ride.
Welcome back to our final deep dive on exoplanets.
Wow, I'm still processing all this amazing information, from scorching hot Jupiters to potentially habitable worlds like TRAPPIST-1. It's been a journey.
It really has, and we've only just scratched the surface.
And that brings us to the next question. Could we ever travel to these distant worlds? We're talking light years. The sheer scale of space is mind-boggling.
It's one of the biggest hurdles for sure. Even with our best tech, it would take tens of thousands of years to reach even the closest star systems.
Tens of thousands of years. That's longer than human civilization has even existed. So are we stuck here, forever gazing at these distant stars? Is there any hope for interstellar travel?
While the challenges are huge, there are brilliant minds working on it. One idea is the generation ship.
A generation ship. Sounds like sci-fi.
It does, right? Imagine a massive self-sustaining spacecraft. A mini city in space, designed to carry thousands of people on a multi-generational journey to another star system.
So not just a spaceship, a whole traveling world.
Exactly. It would require crazy advances in technology, life support, artificial gravity, food production, even social structures, to create a sustainable community over such a long voyage.
It's almost like a social experiment as much as a technological one. Imagine the stories that would unfold in those traveling cities.
Absolutely. And all the questions about how humans would adapt, living in confinement for generations, maybe losing their connection to Earth.
Speaking of adapting, you mentioned directed panspermia.
Ah, yes. The idea of seeding life on other planets.
Instead of sending people, we send microorganisms or genetic material to kickstart life on a lifeless world. Is that even possible?
It's been debated for a long time. Some scientists believe it's a way to spread life across the galaxy, creating new biospheres.
Fascinating, but also raises ethical questions. Wouldn't we be interfering with the natural course of things?
Definitely a valid concern. Do we have the right to alter the biological trajectory of other worlds? It's a question about life, evolution, and our role in the universe.
Big questions for sure.
Big questions.
Okay, let's get back to interstellar travel. We talked about laser-powered light sails and warp drives. Anything more realistic on the horizon?
One exciting project is Breakthrough Starshot. It aims to send tiny laser-propelled spacecraft to Proxima Centauri b.
Proxima Centauri b, the closest one.
Yep, they want to use powerful lasers beamed from Earth to accelerate these probes to a fraction of the speed of light, reaching Proxima Centauri b within a few decades.
A few decades?
Yeah.
That's incredible. What could these probes even do?
They'd have cameras and sensors to capture images, data about the planet's atmosphere, surface, maybe even its magnetic field. Our first close-up look at a planet around another star.
Wow, that's really cool. Actual images of Proxima b in our lifetime. Amazing.
It is. And there are other missions, like the European Space Agency's Plato, designed to find Earth-sized planets around sun-like stars.
So the search for other Earths continues. It feels like we're at the beginning of some huge discoveries in exoplanet science.
Absolutely. With every new finding, every new technology, we're learning more about the universe, how complex and rich it really is.
And as we explore, we face new challenges, new ethical dilemmas, new questions that push us to think bigger and bolder.
It's a journey that will likely continue for a long time, one that could change how we see ourselves and our place in everything.
Well, that wraps up our deep dive into exoplanets. We've explored so much.
Yeah.
Gas giants, rocky planets, hot behemoths, potentially habitable oases. It's been quite a ride.
It really has. A fascinating exploration of what lies beyond our own little corner of the universe.
We learned how astronomers find these planets, thought about the incredible possibilities of traveling to them, and the ethics of it all. It's a lot to consider.
It is, but that's the beauty of science. It's a process of constant exploration and discovery.
And it reminds us that there's still so much out there to explore, so much to learn.
And so much to imagine.
So keep looking up at the stars. Keep asking those big questions.
Yeah.
And never lose that sense of wonder. The universe is full of mysteries waiting to be uncovered. And who knows, maybe one day we'll find ourselves on an alien world, looking back at our own pale blue dot in awe and appreciation.
Until then, keep exploring, keep learning, and keep dreaming of the possibilities. The cosmos awaits.
All right, buckle up, everyone, because today we are diving deep into a brand new cosmic mystery. We're talking about a radio signal from space, and get this, it repeats almost every hour.
Hourly signals from space. That's fascinating.
All right. It's wild. We've got some journal excerpts and news articles hot off the press, and, well, let's just say they're raising more questions than answers.
Well, that's what makes it a mystery, right? I'm ready. Let's unpack it.
Okay, so first things first. This signal was picked up by the Square Kilometer Array. It's also called the SKA. Have you heard of it?
Of course. The SKA is this massive next-generation radio telescope. It's still being built, actually, spread across Australia and South Africa.
Yeah. And even before it's fully operational, it's already making these groundbreaking discoveries. That's how powerful it is.
The SKA is going to completely revolutionize radio astronomy. Just you wait. This is just the beginning.
Okay, so let's break down this signal itself. It repeats roughly every 53 minutes, which is so interesting because it's close to an hour, but not exactly 60 minutes. What's the significance of that?
That 53-minute period, it's a huge clue.
Yeah.
For one thing, it doesn't match up with any known signals coming from Earth. It doesn't line up with our planet's rotation either.
So we can rule out interference like someone's microwave oven or a satellite or something.
Exactly. This signal is coming from deep space. That's why we're so excited about it.
Wow. Okay, now you said earlier that this signal has a distinct structure. What does that actually look like?
Well, think of it this way. Astronomers have found 3 different modes within the signal.
Wait, so it's not just a constant stream of radio waves?
Nope, not at all. There are these periods of silence. Then you get these powerful bursts that can last anywhere from 10 to 50 seconds.
Okay, wow. So silence, then boom, these bursts.
Yeah, and then on top of that, there are these super short flashes, less than a second long, kind of sprinkled in.
So we've got silence, these longer, powerful bursts, and then quick little flashes.
You got it. And it's this whole combination that is throwing scientists for a loop, because it doesn't really match anything we've seen before.
It's like the universe is speaking in code, and we're just trying to figure out what it's saying. Okay, so does this weird signal match any known cosmic radio sources?
Well, that's the million-dollar question, isn't it? And so far, the answer is no. This doesn't fit neatly with the usual suspects. It's something different.
Okay, all right. Well, then let's put on our detective hats. What are some of the prime suspects we should consider?
Okay, well, one possibility is a pulsar.
Those are what are they again?
Pulsars are these super dense leftovers of massive stars that have gone supernova. We call them neutron stars.
Right, and they spin really fast, right?
Yeah, they spin incredibly fast, and as they spin, they send out beams of radiation, and we detect those as pulses.
So could a pulsar be spinning slowly enough to create this hour-long signal? Or is that just not possible?
It would be pretty unusual. I mean, pulsars do slow down over time, but to have a period of almost an hour, that would mean it's lost like almost all of its energy, which would make it super faint, hard to detect.
It's not impossible, but really unlikely.
Yeah, it would seriously challenge our current understanding of pulsar evolution.
Okay, so maybe a pulsar, but one that's acting pretty strange. What else could be causing these hourly signals?
Well, another candidate is a magnetar.
What are?
A magnetar. Think of it like a neutron star, but with a magnetic field turned up to 1,000,000. Trillions of times stronger than Earth's magnetic field.
Well, okay. Strong magnetic fields.
Yeah. And magnetars are known for these crazy, unpredictable bursts of energy.
So could a magnetar be behind this? A slowly spinning one with a super strong magnetic field?
It's definitely a possibility, but we have to be honest, magnetars are known for chaotic bursts, not for these precise, regular signals like we're seeing.
So it'd have to be a magnetar behaving a little differently than we expect.
Yeah, there's some inconsistencies. We need to figure those out.
Got it. Okay, so what other suspects are on our list?
Let's think about another type of stellar remnant, a white dwarf.
Okay, so those are like what happens to smaller stars, right? Like our sun, after they run out of fuel.
Exactly. They're not as dense as neutron stars, but they can still be incredibly powerful.
And they spin, right? So could a white dwarf spin, maybe with the strong magnetic field, be creating this signal every hour?
It's a good thought. It's possible in theory. But the white dwarf radio sources we've seen before, they don't really match this pattern.
So maybe. A type of white dwarf we've never encountered before. It seems like we keep coming back to this idea of something completely new.
And that's what makes this discovery so exciting. It could be something we know, but with a unique twist. Or it could be something totally revolutionary.
I have to ask, with these unexplained signals from space, people are going to wonder about aliens, right?
Of course, that's always a fun thought, the possibility of aliens. But as of now, we haven't found any evidence to support that idea. No patterns or encoded information in the signal that would suggest, an intelligent source.
So no alien messages just yet. But there's still a chance this signal is from something totally new, right?
Absolutely. I mean, think about the history of astronomy, full of unexpected discoveries, things like pulsars, quasars, fast radio bursts. All of those seemed impossible until we found them. This new signal could be our next big leap forward.
Okay, so we've got our potential suspects, some familiar faces, maybe acting strangely, and then the chance of something totally new. What happens now? How do scientists actually go about investigating a signal this bizarre?
It's all about gathering data. Astronomers around the world are going to point their telescopes at this patch of sky and hope to catch more of these bursts.
Like a global scientific team all working together. What are they hoping to learn?
Everything. We're talking the shape of each burst, how long it lasts, what frequencies are involved, even something called the polarization of the radio waves.
Polarization? What's that?
It tells us about the magnetic field surrounding the source.
So it's like building a fingerprint for this mystery object.
You got it. And then as they get more bursts, they'll be looking for any changes over time. Like, do they vary in intensity? Do they happen at slightly different times?
So it's not just catching the signal, it's about how it changes too.
Interesting. Are there any other avenues to look at?
Oh, absolutely. One of the big questions is whether there are any other signals happening at the same time as these radio bursts. Like, are there X-rays, infrared light, visible light? Finding those would be super helpful.
So it's like piecing together a puzzle, using every piece of information to get a complete picture.
Exactly. And that's what makes this so exciting. The more we learn, the more intriguing this mystery becomes. This whole process of investigating this signal, it really reminds me of some of the most exciting discoveries in the history of radio astronomy. There have been so many times when astronomers found these signals that seemed totally baffling at first.
Oh, I bet. Like every new signal is this challenge, pushing us to expand our understanding of the universe. Didn't they used to think that pulsars were alien beacons?
That's right. Back in the 1960s, when they first found pulsars, their pulses were so regular that some scientists really did think they might be picking up signals from an extraterrestrial civilization. Wow, can you imagine the excitement, the mystery? What did those first pulses sound like?
Imagine this steady, rhythmic beat, almost like a cosmic clock ticking away. Super precise. It was unlike anything they had ever heard before.
No wonder they thought it could be aliens. I even read somewhere that they nicknamed the first pulsar signal LGM-1. What did that stand for?
Little green men. I know, right? It's funny to think about now, but it really shows that sense of wonder, that feeling of the unknown that always comes with these big discoveries. Of course, they studied the signal more and more, and they figured out it was coming from a rapidly rotating neutron star, a pulsar.
So a natural phenomenon, but one that completely changed how we understand these super dense stellar remnants. It's crazy how what seems like science fiction one day can be textbook science the next. Are there any other examples of weird signals that turned out to be something amazing?
Oh, absolutely. There's the story of cosmic masers, for example. Early days of radio astronomy, scientists were puzzled by these radio emissions coming from space. They were super narrow band, which was strange.
Narrow band.
Yeah, they were focused on a very specific frequency. It almost seemed artificial because most natural processes produce a wide range of frequencies. But these signals were super focused.
Interesting. So what were they?
It turns out they were like naturally occurring amplifiers in space. We call them masers. It stands for microwave amplification by stimulated emission of radiation. Basically, it's molecules like hydroxyl and water vapor acting like cosmic lasers.
So nature was basically creating its own technology. It's mind-blowing. What other natural wonders are hiding out there?
That's the question, isn't it? And sometimes the explanations are a bit more down to earth.
Wait, are you talking about the microwave oven
Well,
story?
you know it. It's a classic. It happened at the Parkes Observatory in Australia. These astronomers kept finding these weird, short radio signals, and they were convinced it was something from deep space.
And what was it?
A microwave oven in the break room.
No way.
Someone kept opening the door before the timer finished, and the microwaves were messing with the telescope.
That's hilarious. It just shows that even when you're searching for these cosmic truths, sometimes the answer is right there in front of you, but it also shows how important it is to be super careful and rule out all the possible sources of interference.
Couldn't agree more.
Okay, so back to our hourly signal. What's the big takeaway from all these stories, these historical parallels?
I think it's about keeping an open mind. When we find something unexpected, something that challenges what we think we know, we shouldn't just dismiss it, you know? We should be curious, investigate it thoroughly, and be open to the possibility that we might be on the verge of a huge breakthrough.
That's a great point. So let's zoom back in on our mystery signal. Why does this discovery even matter? What are the implications if it really is something totally new?
Think about it. This signal has the potential to completely change how we understand astrophysics. It could give us insights into how stars live and die, the extreme conditions out there in the universe, maybe even weird states of matter that we can only dream of creating in a lab.
It's like getting a sneak peek into a part of the universe we've never seen before.
Exactly. It's what makes astronomy so captivating, right? The universe is vast and full of surprises, and every new discovery, like this hourly signal, brings us a step closer to understanding our place within it. It reminds us that we're still just scratching the surface of what's out there.
I love that sense of awe, that wonder that astronomy inspires. So zooming out a bit, how does this discovery fit into the bigger picture? Like, what are astronomers ultimately trying to achieve?
I think it shows how important it is to invest in these huge scientific projects like the SKA. We're already making these incredible discoveries before it's even fully operational. Imagine what we'll find when it's at full power. It also shows how science brings people together. Researchers from all over the world, pooling their knowledge and resources, working together to understand the cosmos.
And it's not just about understanding the universe out there, right? These discoveries can teach us about physics here on Earth, too.
You got it. By studying extreme environments, like neutron stars and magnetars, we can learn about matter under these incredible pressures and densities that we could never replicate in a lab. It pushes the boundaries of what we know and could lead to all sorts of new technologies we haven't even imagined yet. For example, we wouldn't know nearly as much about nuclear physics if we hadn't studied the processes happening inside stars.
So this isn't just some abstract pursuit of knowledge. It's about expanding our understanding of the universe and potentially creating new technologies that could benefit everyone.
Exactly. And this signal is a reminder that the search for knowledge never really ends. Every step we take, every mystery we solve, opens up new paths to explore. It's about expanding our horizons and inspiring future generations to look up at the sky and wonder what else is out there.
That's beautiful. But before we get too philosophical here, what are the next steps in this investigation? I need to know.
Well, it's still early days. Scientists will be collecting as much data as they can on this signal. They'll be studying it over time, looking for any clues that could reveal its source, and they'll be keeping their eyes peeled for any similar signals from other parts of the sky.
It's like they've opened a new chapter in a cosmic story, and we're all waiting to see what happens next. Any predictions about what we might learn in the coming months or years?
Hard to say for sure, but here are a few possibilities. One scenario is that we get more data and confirm that the source is something we already know about, like a magnetar or a white dwarf, but with some unique characteristics we haven't seen before.
So not a brand new type of object, but like a variation.
Yeah, exactly. It could be a magnetar that spins really slowly but still manages to produce these strong bursts. Or it could be a white dwarf that's part of a binary system with another star that's influencing it somehow.
Okay, that's one possibility. What else?
The more exciting possibility, of course, is that this signal really is something completely new.
Something we've never even thought of before.
Something that forces us to rewrite the textbooks. It would be a total game changer for astrophysics. But even if it ends up being something we already know about, the fact that we're even detecting these signals is amazing. It tells us there's so much more out there that we don't understand.
It's a good reminder that the universe is full of mysteries, and we're just starting to uncover them. It really is an exciting time for astronomy. This whole deep dive has been incredible. All this information, all these possibilities. It's clear that this investigation is just getting started, and who knows what amazing things it might reveal about the universe we live in.
Astronomy is in such a thrilling era right now. I think this discovery, no matter where it leads us, tells us something really profound about where we fit in the grand scheme of the cosmos. It's a reminder that we live in this massive universe, everything's interconnected, and we're always pushing, always trying to understand more and more. Every signal we find, every discovery we make, it expands our understanding of the universe, but also of ourselves,
Yeah, I love that. It's like each new piece of information we find, it's like adding another thread to this intricate tapestry, the universe. And the more we learn, the more we realize just how much more there is to learn.
Exactly. And it's a picture that's always changing, always evolving. Every new discovery helps us refine our understanding, and sometimes we even got to throw out old ideas and embrace new ones. That's the beauty of science, always moving forward, constantly learning and questioning and exploring what we don't know.
That's what makes it so exciting. We're not just sitting back and watching the universe. We're trying to figure it out,
Yeah.
It's like we're part of this cosmic conversation, and every new signal is a message waiting to be decoded.
I like that. A cosmic conversation. And this conversation, this understanding, it can change so much. Not just our scientific knowledge, but our technology, our philosophy, even our art. Think about how when we discovered other galaxies, it totally changed how we see our place in the universe.
Right. Or those incredible images from the Hubble Space Telescope. They've inspired so many artists and musicians and writers. It's amazing how science and art, which people sometimes see as separate things, are really connected deep down. They both come from that same human curiosity that need to make sense of the world.
I couldn't agree more. And this new signal, this hourly signal, however it turns out, it just shows that human spirit of exploration, that drive to understand, to discover, to push the boundaries of what we know, is part of what makes us human.
I feel like this deep dive has really shown that. I can't help but feel this sense of wonder, this excitement. What if this really is something totally new? What if it unlocks this whole new understanding of the universe?
It's a pretty amazing thought, right? The idea that we might be right on the edge of a huge scientific revolution. And even if it turns out to be a variation of something we already know, the fact that we're even detecting these signals is incredible. It's a testament to human ingenuity, our ability to figure out these cosmic mysteries.
It's humbling too, isn't it? The universe is always there, reminding us how vast and complex it is, and yet it also inspires us. It makes us want to keep searching, keep asking questions, keep pushing those limits.
I couldn't have said it better myself. This quest for knowledge, it's a journey that never ends. And we're not just doing it for ourselves, but for the generations that come after us. Every discovery leads to new discoveries, and that's what makes it so rewarding.
You've put it perfectly. This is what makes this whole deep dive and astronomy in general so fascinating. It's not just about the facts, it's about that sense of wonder, that drive to learn, that realization that we're all part of something so much bigger than ourselves.
As we keep exploring, who knows what other mysteries we'll uncover, what wonders we'll find, what questions we'll be inspired to ask. That's the beauty of it all. It's about the journey, just as much as it is about the destination.
So, to our listener, as we leave you to ponder this cosmic signal and all it might mean, we hope you'll hold on to that sense of curiosity. Look up at the stars. Remember that we're all part of this incredible dance of the cosmos. And never forget that there's always more to discover out there. Until next time, keep exploring, keep asking questions, and never lose that sense of wonder. All right, so buckle up, everybody, because today we're taking a deep dive that takes us right to the edge of the universe, or at least to the edge of what we currently know about it. We're going to grapple with a question that's really puzzled humans for, well, probably as long as we've been looking up at the stars. Does the universe have an edge?
Yeah, that's a great question. And it's one that leads to some really mind-bending paths, as I think you'll see from the excerpts you've shared.
Okay, so before we get lost in all of the truly cosmic stuff, let's actually start with something a little closer to home, something we can actually observe. You know what I'm talking about? The observable universe. So what exactly is that, and why is it so important for us to understand?
Well, you can kind of imagine the universe as this vast space that's constantly expanding outwards, right? So the observable universe is basically our limited view of that space. It's this bubble that's centered around us, defined by the distance that light has had the time to travel since the Big Bang occurred.
So it's kind of like our cosmic horizon in a way.
Mm-hmm.
But it's not actually a physical wall or anything like that, right?
Exactly. You got it. It's just the limit of what we are currently able to see. And this is where it gets interesting. Different telescopes can actually see different eras of the universe because they can actually detect different wavelengths of light. You know, think about the James Webb Space Telescope. It can peer into the infrared, so it's detecting light that has been stretched and redshifted over billions and billions of years, allowing us to glimpse some of the earliest galaxies in the universe.
Wow, that's really amazing. But even with these incredible telescopes that we have, I imagine that it's still pretty tricky to actually measure the distances and the ages of these objects that are, billions of light years away from us.
Oh, absolutely. It is a huge challenge, one where we need a ton of precision to get it right. We rely heavily on something called spectroscopy. That's basically analyzing the spectrum of light to avoid errors. As the universe expands, you see the light traveling through it gets stretched, and this shifts its wavelengths towards the red end of the spectrum. That's what we call redshift.
Okay, yeah, I've definitely heard of redshift. But what's so important about getting that redshift calculation right?
Well, just think about it this way. If we miscalculate the redshift, we end up with an inaccurate picture of how far away something actually is, and therefore how old it is. And even a small error in that calculation can actually snowball into a huge misunderstanding of the entire universe's timeline of how galaxies have evolved over time.
So like one tiny decimal point is off, and all of a sudden we think a galaxy is from a completely different era of the universe.
Precisely. And there was actually this fascinating case where an object was initially thought to have a redshift of 16. And that suggested that it existed just a couple of 100 million years after the Big Bang. I mean, it was practically a baby picture of the universe.
Wow, that would have been huge.
It would have been. But more detailed analysis actually revealed that the actual redshift was more like closer to 5 or 6. Still incredibly distant, don't get me wrong, but not quite as groundbreaking. This just goes to show how crucial it is to carefully validate those measurements and not jump to conclusions too quickly.
So, lesson learned when it comes to the distant universe.
Yeah.
Always double-check those cosmic measurements. Okay, but let's say we've accounted for redshift and all of that. Does the edge of the observable universe mean that there's like an actual edge to the universe? Like if we kept traveling outwards, would we eventually hit a giant wall somewhere?
Well, that's a pretty common misconception that a lot of people have, but thankfully that's not what our current cosmological model suggests. There's likely no such boundary in the four-dimensional space-time continuum.
Okay, so no cosmic brick wall. That's a relief. But how can we even wrap our heads around the idea of a universe that just doesn't have an edge? It's kind of mind-boggling, to say the least.
It is. Well, think of it this way. Imagine a two-dimensional being that lives on the surface of a sphere, right? They could walk and walk forever and ever, and they would never actually hit a physical edge. But we as three-dimensional observers can see that the sphere itself is actually finite.
So maybe the universe is finite, but our three-dimensional brains just can't quite grasp it.
It's a fascinating possibility for sure. And this is where things get even more intriguing. Not only is there likely no edge, but the universe is constantly expanding. And it's not just the stuff in the universe that's moving apart, it's space itself that is stretching.
Wait, so it's not like an explosion where everything is flying outwards from a central point?
Not at all, no. It's more like imagine a loaf of raisin bread dough that's rising in the oven, right?
Yeah.
Each raisin, and the raisins would represent a galaxy, in this case, is getting farther away from every other raisin, but there's no single center of that expansion.
Okay, I think I'm starting to get it. So every single point in the universe could actually be considered the center from its own perspective.
Precisely. Which also means that during the universe's early period of rapid inflation, the expansion might have been happening even faster than the speed of light.
Hold on, faster than the speed of light, but isn't that like the ultimate cosmic speed limit?
It is pretty mind-blowing, right? But it doesn't actually violate the laws of physics because it's not matter moving through space faster than light. It's space itself that was expanding at that insane rate. Think of it like stretching a rubber band with dots on it. The dots aren't actually moving themselves, but the space between them is increasing.
Okay, my brain is definitely starting to bend here a little bit. But all this talk of expansion, especially at those extreme early stages, it makes me wonder about the role of gravity. Wouldn't gravity have had a huge impact on all of this?
That's a fantastic question, and it leads us right to the edge of our current understanding. Einstein's theory of general relativity, which explains gravity beautifully on large scales, actually starts to break down when we try to apply it to incredibly dense environments, like the very, very early universe or black hole singularities.
So, like, we need a whole new theory of gravity in order to fully grasp what was going on back then.
That is the quest, my friend. Physicists all over the world are actively searching for what they call a quantum theory of gravity. It would be a theory that could reconcile general relativity with the principles of quantum mechanics. It's one of the biggest mysteries in all of physics today.
And what about this graviton I keep hearing about? Does that play into this quantum gravity puzzle at all?
Ah, yes. Well, the graviton is a hypothetical particle. We haven't actually been able to detect it yet. But if it does exist, it would be the particle responsible for actually mediating the force of gravity, much like the photon carries the electromagnetic force. And scientists are currently studying gravitational waves, those ripples in space-time that are caused by massive objects, and they're hoping to learn more about gravity's quantum nature and maybe, just maybe, even find evidence for the graviton.
It's amazing to think that by studying these huge cosmic events, we might actually unlock the secrets of gravity itself. But we can't talk about the structure of the universe and its evolution without talking about the elephants in the room here. I'm talking about dark matter and dark energy.
Ah, yes. Two of the biggest mysteries in cosmology. They're called dark because we can't directly see them. They don't interact with light in the same way that normal matter does, but we know they must exist because of their gravitational effects.
So we can't see them, but we can see what they're doing.
Exactly. Dark matter, for example, seems to be what's holding galaxies together. We see its gravitational pull on the stars and gas, even though we can't detect the matter itself. And then there's dark energy. Now that's even more baffling. It's this mysterious force that's actually causing the expansion of the universe to speed up, to accelerate.
So not only is the universe expanding, it's actually expanding faster and faster, and we have no idea why.
You got it. That is the big mystery. There are lots of theories out there, of course. Some think that dark matter could be made up of some exotic particles that we haven't discovered yet. Maybe dark energy is related to a cosmological constant, or perhaps even some entirely new kind of field that permeates all of space. It's all very much an open question at this point.
Okay, my brain is officially hurting, but in a good way.
Yeah.
It's incredible to realize just how much we still don't know about the universe. But before we get too lost in the cosmic depths, I kind of want to bring this back down to our own little corner of the universe for a second. Where exactly do we fit into this vast, expanding web of galaxies and dark matter and all of that?
Well, our own Milky Way galaxy is actually part of what we call the local group. It's a collection of about 100 galaxies that are gravitationally bound together. And the local group itself is actually part of the even larger Virgo supercluster, which is just one tiny node in this vast cosmic web that extends across billions and billions of light years.
Wow, talk about a cosmic address. The Milky Way, the local group, the Virgo supercluster.
Yeah.
It really puts things into perspective, doesn't it?
It really does. And it just highlights how vast and complex the universe truly is.
Yeah. But if the universe keeps expanding the way we think it will, what happens to all those distant galaxies? Will they eventually just drift so far apart that we can't even see them anymore?
Now, that's a question that really takes us to the very edge of what we currently know about the universe, and it's one that we'll explore further in the next part of our deep dive.
Okay, so we've talked about this incredible, ever-expanding universe and the fact that it probably doesn't have an actual edge. But you left us hanging there with that cliffhanger about those distant galaxies maybe fading from view at some point. What does it actually mean for us? For our understanding of the cosmos, if those galaxies were to just disappear?
Yeah, well, just imagine a future, right, where the light from those distant galaxies has redshifted so far that it's become completely undetectable, even to our most super advanced telescopes. We'd essentially be stuck with only our own Milky Way galaxy to study.
Wow. I gotta say, that's kind of a lonely thought. Like going from this grand panoramic view of the universe to basically staring through a tiny little keyhole. What would that do to the field of cosmology? Our ability to understand how the universe works as a whole.
It would certainly limit our perspective, that's for sure. And it would definitely force us to, rethink a lot of our current approaches. A lot of the techniques that we rely on today, like measuring the cosmic microwave background radiation or observing those distant supernovae to track how the universe is expanding, all of that would become basically impossible.
So we'd lose access to some of our most powerful tools for understanding the universe. That sounds like a pretty major setback for science.
It would definitely be a challenge, yeah. We'd be left with this much more localized view. And trying to piece together that bigger picture, of the universe's history, how it's evolved over time, it would become much, much harder.
So, future generations of scientists might be stuck with an incomplete view of the universe, maybe even an inaccurate one.
It's definitely a possibility, but I also think it would spark incredible ingenuity. Humans are amazingly adaptable,
Right.
I can totally imagine future scientists developing entirely new technologies and techniques that could, maybe allow them to detect incredibly faint light that's been redshifted to extreme degrees, or maybe they'd find ways to study the universe through, I don't know, gravitational waves or other phenomena that we haven't even fully grasped yet.
So it's not necessarily game over. It's more like, level 2 of the game has started with a whole new set of rules and challenges.
Exactly. And remember, even if we were limited to only observing our own galaxy, there's still an incredible amount that we don't know about the Milky Way itself. We're constantly discovering new stars, new planets, even entirely new structures within our galaxy.
That's a really good point. It's easy to get caught up in, the vastness of the universe and forget that there's still so much to explore right here in our own cosmic backyard.
Absolutely. And who knows, maybe by delving deeper into the intricacies of our own galaxy, we might uncover clues that could actually help us understand the broader universe in ways that we can't even imagine right now. It's kind of like, becoming an expert in a single complex ecosystem. That expertise can often shed light on the workings of larger interconnected systems.
Okay, that's actually a really encouraging thought. But let's just step back for a minute here and talk about some of the other theories that are out there about, the universe's ultimate fate. Earlier, we were talking about this idea of perpetual expansion. But weren't there some other possibilities too? What about the Big Crunch?
Right, the Big Crunch. Yeah, that was a pretty popular idea for a while. It basically imagined a scenario where gravity eventually wins out over this expansion, pulling everything back together into a super dense singularity. Essentially like a reverse Big Bang.
So the universe would basically just collapse in on itself. That sounds pretty dramatic.
It does, yeah. But based on what we currently know about dark energy and the fact that the expansion seems to be accelerating, the Big Crunch just seems a lot less likely now.
Okay, well, what about the Big Rip? Now, that one sounds even more intense. What's the thinking behind that one?
Oh, the Big Rip is a wild idea. It basically suggests that dark energy could, at some point, become so incredibly powerful that it literally rips apart everything. Galaxies, stars, planets, even atoms themselves.
So it's like everything would just disintegrate.
Huh.
Okay, that's kind of terrifying, but I got to admit, it's also kind of awesome.
Yeah.
In a cosmic, destructive sort of way.
Yeah, it's definitely a very dramatic scenario. But like the Big Crunch, it's not really the most favored hypothesis based on the data that we have right now. Perpetual expansion, fueled by dark energy, still seems to be the most likely path for the universe, at least for now.
Okay, so maybe not a super fiery or cataclysmic ending, more of a slow, gradual fade into cosmic isolation. But
Yeah.
You said based on current data there. So does that mean our understanding of all this could still totally change? What if there's some other force or factor out there that we haven't even discovered yet? Something that could just throw everything we think we know right out the window.
Well, that's the beauty of science, right? It's constantly evolving. It's a process. Our understanding of the universe has already changed drastically over the past, 100 years. And there's really no reason to think that it won't continue to change in the future as we learn more.
So the ultimate fate of the universe is still very much an open question. That's exciting.
Yeah.
And also a little bit unsettling at the same time.
Absolutely. And that's what makes cosmology so captivating. We're constantly pushing the boundaries of what we know, trying to piece together this immense puzzle of the universe's origin, how it evolved, and ultimately, how it will all end.
And who knows what incredible discoveries await us in the future. Maybe we'll find a way to overcome those limitations of the observable universe, or unlock the secrets of dark matter and dark energy.
The possibilities are truly mind-boggling, but, even if the universe is ultimately destined to just slowly fade into darkness, I don't think that has to mean it's a sad ending or a meaningless one.
I love that perspective. It's not about the end. It's about that incredible journey of discovery and understanding. So where do we go from here? We've covered a lot of ground today. From the edge of the observable universe to those mind-bending ideas about expansion in space-time, the mysteries of dark matter and dark energy. We even touched on some of those potential fates for the cosmos, what they might mean for future generations of, cosmic explorers. So what are the key takeaways here for our listeners?
I think the most important thing for people to remember is that our understanding of the universe is always changing. It's fluid. What we think we know today might be completely overturned tomorrow. So it's so important to stay curious, to keep asking those questions, and be open to new possibilities.
So stay curious, keep exploring, and never, ever stop being amazed by this universe and all of its mysteries. Wow, we've really been on quite a journey, haven't we? Exploring the universe, from the edge of what we can actually see to all these mind-blowing mysteries about dark matter and dark energy and how it's all going to end. It really makes you realize there's just so much out there.
It really is humbling when you think about it. And like we've been talking about, the universe is constantly doing its thing, evolving, expanding, and just always throwing curveballs our way.
Totally. But before we wrap things up, I wanted to circle back to something you mentioned earlier. This idea that if the universe keeps expanding like we think it will, we could actually lose sight of all those other galaxies out there. So what happens to, our whole understanding of the universe then? Are we just, stuck with this limited, cosmic tunnel vision forever?
Yeah, it's an interesting question to think about, isn't it? Imagine future astronomers, right? They're gazing up at the night sky, and all they see are the stars of our own Milky Way. It would be a pretty profound shift in perspective, I think.
Yeah, it'd be like, I don't know, going from exploring this vast, vibrant rainforest to just studying a single tree in your backyard. You might learn a lot about that one tree, but you're missing out on this whole incredible ecosystem.
That's a great analogy. And it really highlights, I think, the challenges that future cosmologists might have to deal with, think about it. A lot of the techniques that we rely on today to study the universe, on this grand scale, they would become totally impossible if those distant galaxies just faded from view.
We wouldn't be able to use those distant supernovae to measure the expansion rate of the universe anymore.
Exactly. And studying the cosmic microwave background radiation, that afterglow of the Big Bang, it would be much, much more difficult to study that as well. I think we'd be left with a really localized view and piecing together that larger story, the history of the universe, how it's evolved over time. It would become a really, really hard problem.
It kind of makes you wonder if we're living in this sort of golden age of cosmology, you know what I mean? We have this incredible window to see so much of the universe, a window that might not always be there.
Yeah, that's definitely a possibility. We might be living in this unique time when the universe is basically revealing all these secrets that won't be accessible to those who come after us.
But that doesn't mean those future scientists will just give up, right? Humans are amazingly creative. I can totally imagine them coming up with all sorts of, creative new ways to study the universe, even with those limitations.
Yeah. Oh, for sure. Necessity is the mother of invention, right? So who knows? Maybe they'll figure out how to build telescopes that can detect these incredibly faint signals. Or maybe they'll find ways to study the universe through, subtle variations in gravity or something. Or maybe they'll even learn how to exploit quantum entanglement for astronomical observations.
Now that would be mind-blowing.
Yeah.
It makes you wonder if those future discoveries, whatever they are, could end up completely revolutionizing our understanding of the universe, just like the invention of the telescope did centuries ago.
It's definitely an exciting prospect. But even if we are eventually limited to just observing our own galaxy, there's still so much that we don't know about the Milky Way itself. I mean, we're discovering new stars, planets, black holes all the time. We're even finding entirely new structures within our galaxy that we never even knew existed before.
It's like we've only just scratched the surface of our own little cosmic neighborhood.
Exactly. And who knows, maybe by delving deeper into, the intricacies of our own galaxy, we might actually find clues that unlock even bigger mysteries about the universe as a whole.
It's like it's all connected, right? The really small stuff to the really big stuff. What's happening here in our own little corner of the universe to what's happening billions of light years away. It's like each new discovery, no matter how small it seems, adds another piece to that huge cosmic puzzle.
I love that. And that's really what makes all of this so fascinating. The universe is just this incredibly vast, interconnected web of wonder, and I think we're just barely beginning to grasp just how complex it really is.
It's been an amazing journey, that's for sure. Exploring the edge of what we know, maybe even pushing past that edge a little bit. We talked about the observable universe, some of those truly mind-bending ideas about how space and time work, and the mysteries of dark matter and dark energy. We even got to ponder the ultimate fate of the universe and what it all might mean for those future generations of, cosmic explorers out there.
Yeah, and I think through all of that, the biggest takeaway is this. The pursuit of knowledge, it's a journey that never really ends. There will always be more questions to ask. There will always be more mysteries to solve. And there will always be new frontiers to explore.
So, to everyone listening out there, keep looking up, keep asking those questions, and never ever lose that sense of wonder and curiosity about this incredible universe that we all get to call home. This journey of discovery is far, far from over.